This video will be an informal discussion of some of the aspects of Bayesian inference. So Bayesian inference is a very large field, so this will be just a sort of 10,000 at the 10,000 foot level. And so first, what is Bayesian inference? Roughly speaking, in Bayesian inference, we assume a prior distribution. Bayesian inference always assumes some prior distribution on parameters theta. So you're usually working with some, distribution on some observables given some parameters, and you assume a distribution over these thetas. And then you just use the rules of probability to answer whatever questions, to infer the answers to whatever questions you're interested in. Now, closely related is Bayesian decision rules or Bayesian procedures. So if you minimize, in decision theory, you minimize expected loss. And if you minimize expected loss where you're also averaging over this, averaging over theta using the prior distribution, averaging over theta, then this is called a Bayesian procedure. So you're averaging over everything, really, in this expectation. Now, you may have heard of a distinction between different types of Bayesian approaches or Bayesian people. One type is called objective Bayes, and the other is subjective. So if you watch the little video of the simple example of estimating the length of a football field that I gave in another video, that's an example of a subjective Bayes type of approach, in which you choose a prior that's based on your beliefs. So it's a belief-based prior. You choose a belief-based prior. So it's subjective. On the other hand, objective Bayes, or what objective Bayesians do, is they say, I don't want to be, we want to be able to agree on what is the right prior. And here, different people in the subjective approach, different people could just choose different priors, and you have no way of sort of determining which is the right one. So objective Bayesians have a solution to this, which is what they call non-informative priors. And in some sense, a non-informative or uninformative, sometimes people say, an uninformative prior, in some sense, it says as little as possible about theta, about the distribution of theta. And there's some subtle aspects to doing that, to coming up with these non-informative priors. And but this is sort of roughly the distinction between these two camps in Bayesians. So let's talk about some pros and cons, some advantages and disadvantages of Bayesian approaches. So pros, first, one really appealing thing about a Bayesian approach is that you can directly answer the questions that you're interested in. For example, if you were trying to measure say the length of a football field or whatever it is, and you wanted to say what's the probability that the length is between 99 and 101, then you could do that directly. You could answer that question directly. Whereas I'm not going to go into detail on the comparison with frequentist approaches, but if you were not assuming a prior distribution, the typical thing that people do is, using the frequentist approach, they would use something like a confidence interval. would be another way to answer this sort of question. Actually, I mean, in Bayesian approaches, they usually use the alternative to confidence intervals is what's called credible intervals, but they're roughly trying to answer this sort of question. And you can't answer this question unless you assume a prior distribution, because otherwise this statement is meaningless, right? If theta is a fixed true value, then either it's between 99 and 101 or it's not. So the probability would be 0 or 1. What you really are asking when you want to know what is this probability is in some sense based on the information that you have, what do you think the probability is, not what the probability of the true value is, not what the true value is actually between these. So that's an appealing thing, and you can just use the rules of probability to directly answer these questions once you assume a prior. Another thing which is nice is that you can avoid some of the pathological behavior associated with frequentist approaches. Let's say pathologies. Avoid pathologies. There are some classic examples. There's a whole world of back and forth between Bayesian and frequentist approaches over the years, and one of the things that has been observed is that frequentist approaches exhibit certain pathologies, certain very strange behavior under certain circumstances, and these can often be avoided with a Bayesian approach. Another nice thing is that by using a prior, you can often avoid overfitting if you're trying to estimate these thetas, or more generally, if you're trying to do some inference, then you can oftentimes, by choosing an appropriate prior, it allows you to avoid overfitting, which could occur in, so for example, if you were using maximum likelihood estimate or something like that. And one more thing, one more pro here, one more advantage, is that a Bayesian approach allows you to, in some sense, automatically do what's called model selection. If you are comparing different alternative models, then Bayesian approaches will, in some sense, automatically prefer simpler models. So in some sense, so this is sometimes referred to as Occam's razor. So it's sort of an automatic Occam's razor. Those are some pros. Now, what are some cons? There must be some cons, and of course there are. Cons? Well, first of all, I mean, the most obvious one is that we have to assume a prior. And especially in the subjective case, this is an unfortunate thing. And even in the objective case, sometimes there's no proper prior which satisfies all the conditions that you would want. So you have to make some, if you want a proper prior, at least that is a prior that integrates to 1, it's a probability distribution, then there's not always a natural objective choice. And another con is that oftentimes exact computation of, so I'll just say this, exact computation can be intractable. Oftentimes when we're doing Bayesian inference, we have to compute the we always have to compute the posterior distribution, and then often we have to do some integral with respect to that posterior distribution. We have to, take an expectation with respect to the posterior distribution. And that doing those operations oftentimes for interesting models can be very they can't be done analytically, and if you were to try to do them on the computer, it would take you way too long. So oftentimes you have to resort to approximations, and that's a disadvantage. Okay, so let me mention one more thing here, which is since these priors are so important in Bayesian approaches, what are some of the different types of priors? There's different types of priors that people use. They sort of can be classified in different ways, and I just wanted to mention briefly what some of them are. So first, well, I already mentioned a non-informative prior or uninformative prior. This is one class of priors. And I already mentioned what those are. So another, well, a specific type, well, often improper priors are used when you're trying to get a non-informative prior, and an improper prior, all that means is that it's a probability, well, it's not a probability distribution. It's improper. So an example would be if you wanted to, for example, if you had a Gaussian distribution, like, how we were, well, what's another example? Say you're trying to estimate the location of something, some parameter theta, and it's a real value, and you want to put a prior on it that makes no assumptions about the location of this parameter. So in order to do that, roughly, I mean, basically what you want to do is you want to have a constant prior. You want to have a prior which is invariant under translations. It's invariant under adding and subtracting. And the only way to do that, if this is 0, this is theta here, this is my real axis. The only way to do that is to have a prior that's represented by a constant, to have a constant prior. But the problem is that on the real line, you can't have a constant function that integrates to 1. I mean, yeah, right, you can't have a constant function that integrates to 1. So in particular, there's no probability distribution that satisfies that. And that's called an improper prior. So like p of theta equals 1 would be an example. On the other hand, you can, even if you take an improper prior like this, oftentimes, sometimes at least, when you compute the posterior distribution, it does turn out to be a proper distribution, and so everything ends up working out sort of okay. Another type of class of priors is what's called conjugate priors. And these are very nice to work with. They have some nice properties that allow you to compute the posterior distribution exactly. So we'll talk more about conjugate priors in the future. All right, so this was the broad outline, in broad brushstrokes, what some of the different aspects of Bayesian inference are. And oh, one other pro. Oh, so I didn't mention one other very important pro here. Yeah, I did. Somehow I missed it. So I didn't have defined admissible procedures, but Bayesian procedures, remember, Bayesian procedures were the ones that minimized your expected loss when you're averaging over everything, including theta. And Bayesian procedures are oftentimes admissible. And admissibility is, without going into the details, roughly what it means is that there's no other procedure which is always better in some sense. So it's not necessarily always the best, but it's not, there's not another one that's uniformly better than that. So it's admissible in some sense. That's what they call it. All right, so that's the broad outline of aspects of Bayesian inference, some pros and cons, and some priors.